So, good afternoon, everybody. Thank you all for attending this presentation. I know it was a long day, so thank you for your patience. My name is Rocco Ascione. I'm a logistic manager of the Italian program. And we managed together with the French program, our colleagues, Concordia Station at Domsey on the high plateau. Before to start, I wish to underline that all the results that I'm going to present you today are very strongly related, linked to the specific environmental condition that we have at the station. At Domsey, the Domsey site, that actually are very harsh conditions, tough for life of people, tough for working activity, but indeed it seems that are very good conditions for this kind of infrastructure. So the reason why we started to do this activity is linked to the big request from science. So it's related to supporting science on the high plateau, and mainly for the big request from very valuable projects like the glaciologist project. The big request is for to have long-term storage for valuable samples that are mainly related to deep drilling projects that are, of course, ice cores drilling projects. In this slide, you see some that we actually have at Concordia. It's an old project, Epica project, but this is the actual archive that we have in Concordia, the ice core archive. It's an old structure, an old infrastructure, but of course is something that we need to replace in the future because this structure is getting older and older and is sinking in the ice. This big storage is made in two parts. The first part is built using a big metal pipe, and this pipe has only the top part, while on the floor there is no structure. So the big problem here is that the pipe is sinking in the ice year by year, and the gap between the top and the floor is getting closer and closer year by year. This is not the main storage of the ice core. At the bottom of this trench, we have this door, and after this door, we have the actual archive of the ice cores. And here you see the situation. Of course, those are the boxes where we have the ice cores from the old Epica project. But you see the conditions, so it means that in a near future, we need to replace that. You see that here that we have underground facilities for this, because the underground facilities on the high plateau are natural storage for this kind of samples, because we have we have a natural storage at minus 50 degrees or below that we don't need to power for its running. Of course, we have again the further projects beyond the Epica project, that is, and this is actually still running on a site called Little Domsey that is very close to Concordia Station. And in this picture you see the boxes with the ice cores that they collected last year, the past summer campaign at the drilling site. Of course, we have the same request to build up a facility for the long-term storage of these samples in Antarctica. Last but not least, we have other big projects, challenging projects, that because all of these projects require big logistics to be implemented, but also to maintain the archive in Antarctica in the future. And this will be really challenging because we require big facilities. The idea of the balloon caves in the polar region is not original from what we did in Antarctica. We have many examples in the Arctic, mainly in Greenland. Here you see some example of ice caves built at East Grip, or they did also some other previous testing at Nîmes. Of course, the environmental conditions in that sites are completely different from the high plateau in Antarctica. But it's, from this picture, you see that what is the main problem of this facility. In a few years, seen from the construction, in a few years, you see the roof of this facility that is getting the distance. The roof is lowering and lowering year by year, and in a few years, the roof is closing. So it's not only a matter of how long can last the facility itself, but it's also a matter of safety. No? In this graph, you see some results of the testing that they did at Nîmes. The blue line and the red line are the two trenches that they did. And also in this graph, you can see the comparison also with other standard trenches made with standard containers, standard shipping containers, so with the metal structure buried in the snow. The trend is almost the same, and in a few years you have a lowering of the roof of meters. But so that's why we started to test the construction of this facility in Concordia. Actually, we did the first test cave. Is the map of a view of the station, the two main buildings. This is the logistic area, and this is the scientific area, a part of it. So we did the first test with a balloon cave, which diameter, the section has a diameter of 5 meters, and it's 15 meters long. But this is just a test. This is a logistic facility with a cave that has the same diameter, but is 35 meters long. And we use this facility as a garage for the winter period. Lastly, last year we built up this additional cave that is the actual archive for the beyond epical ice cores. The two caves have the same dimension, and actually in this cave we have the ice core from beyond Epica project. Here you see some steps of the building of the ice cave. The principle is very simple. To dig out by using a big snowblower, a big trench, very deep trench. Then you put inside a big balloon, inflate the balloon, and then after this you blow up again over the balloon the snow, okay? And at the end you have the buried balloon. Then deflating the balloon, you see, will remain the shape of the cave, okay? It's really important to underline that we have this kind of shape and also the condition of the blown snow that are very specific, the density, the compactness, and also the structure itself. It's really related with the temperature that we have all year long in Antarctica, because basically all the process is based on the sintering of the ice at that temperature. In this additional picture, you see the condition of the cave with the vehicle inside at the beginning of this winter. When we close it, and the main difference you see it's due to the growing of these ice crystals from the top, and this is mainly due to the humidity presence in the air because we open it. So very quickly, here you see the escorts in the additional cave, and the main difference between them is that this is supposed to stay closed all the time with a small entrance, with a small door to enter it, because we don't need to enter this cave with vehicles. And also, the main difference is the shape of the trench that we use to build up the cave itself. That is different. Then we will see in the next slide the difference. So, because now the question is how long we can last this kind of structure in Antarctica, mainly compared to what happened in the Arctic. This is the monitoring plan we are still implementing, and we will continue to implement in the next years to follow up and to have an idea what can be in the future. First of all, we measure the density to understand the evolution of the ice on the top. That is a key point for the study. Then, of course, we monitor the temperature inside the cave. That is also, this parameter is linked to the evolution of the ice. And also, we measure the deformation to understand, also for a safety point of view, what is going on the deformation of the roof and the condition of the shape itself. Then we did, with the help of our French colleague, a simulation study to have a sort of prediction of how long can last this kind of structure. So here some picture of the drilling to measure the density on the blown snow, so actually on the material that is on the roof of the caves. Here we have two different drilling because we have a section in which we have the steps for the T-shaped trench, and a section where it's a wide trench without the steps on site. So here are the values of the density. Here the main difference is that, of course, this is the density on the side of the blown snow, and here this is the value of the normal snow of the untouched ice that has not been managed, groomed by the machine. It can seem that there is a little difference, but this is the key of the strength of this structure. In this situation, the ice look like concrete. This is the results of the simulation study. For this study, they used all the environmental parameter and also the density value that we have that we measured on the caves, and with also different section. This is the narrow section, this one. So you see that the situation. This is the wide section in which the balloon won't touch the walls. But this is challenging for the building process because you can imagine that's a so huge balloon, and you have to put exactly in the middle of the section, and of course it will be moving during the blowing. No, so it's the easiest one is the T-shape because during the process it will stuck on the two walls at the bottom, but of course it has a difference, no, in terms of deformation. You see 3 steps, and at the step of the construction, 50 years after the construction and 100 years after the construction. You see that there is a significant difference of what we have here compared to what happened in the Arctic. Here we are speaking about of decades. And if you consider the two sections, we have a still good condition also after 50 years. So let's say, to have a reference and to confirm the data that we had from the deformation, we did additional measurements of the density on a reference site that is the embankment of the station. You see here in this map the two towers and the location of the two drilling sites where we measured actually the density. And from the values, you see that are really comparable to the one that we measured on the ice cave. But what is important to underline is that this embankment was built about 25 years ago. So after about 10 years and after about 20 years, even more, the values of the density are still the same. So this is really important, and this is a very strong confirmation of what we have from the simulation results. Okay. Again, another confirmation is that this is the measure of the temperature inside the cave. That is about at the middle of the section of the cave. And you see, probably you cannot see perfectly the values here. The values all year long, here you have the month, okay? The values range between the values of -48 and -56, -58. So comparing to the temperature of the air outside, all year long, we have that we are in this area, in this range. So it means that the temperature inside is not affected at all from the temperature outside. And this is good for the storage of the ice cores, because we need a temperature below -50 all the time. And also a constant temperature inside guarantee a long-term perspective of the structure itself. Here is just a very quick animation, just to show you what is the results of the deformation measurement. In this, what we see in this animation is the cloud of points measured using a laser scanner. And this is, of course, a picture at a certain time. In this case, is the picture, the shape at time 0, that means just after the construction. So by comparing the same measurements, the same cloud of points, but taken in different moments, we can, and comparing the different cloud of points, it's possible to measure this deformation. So this is what we had after 1 year from the construction, and the value is about, this value actually is comparable with the value that they had in Greenland the first year, okay? But this is really interesting to see that after a few years, this is the third year of the life, but this is the same values we had after in the first year. The values are almost 0, even because we have to consider that when we measure at different time, different years, we have the effect, we are measuring also the shape of the ice crystals inside. And the dimension of these ice crystals now are about 5 to 6 centimeters. So we cannot say, okay, it's not perfectly 0, but is lower and lower than what they had in Greenland. So this is a good perspective, because it seems that it's going toward the direction of the simulation. Anyway, what we can improve for the future? Of course, we can improve the building technique. We considering different shape or different kind of balloons, but then also we can improve, especially for the future project, big project that will require big facilities. We can improve the construction technique, and also we call it this concept the chromosome concept. And in this animation, you see quickly what is this concept is. This will improve a lot the logistic efforts to have so many caves on the same site. And also reducing the effort to have a similar facility, same facility, in example, the vertical access here, within this vertical balloon, to enter at the same time in 4 different caves. So that's all. Greetings from Concordia Winter Over Q.